In this video, we're going to take a look at rotational inertia. And we briefly mentioned rotational inertia for Newton's, whenever we derived Newton's second law for rotation. And at that time, we looked at it only as a point particle because inertia by definition is just a resistance to change in motion. That's how we defined it whenever we looked at translation. Well, when we look at rotation, it's going to depend on more than just the mass of the object when it comes to how difficult it is to cause a rotation. And you could do this yourself very simply at home by just getting a long heavy stick or even a broom or something like that. And if you hold the broom in your hand close to the bristles, you'll see that it's very easy to just twist the broom and do a rotation with it, like you're twirling a baton. But if you hold it all the way out on its very edge, you're going to have quite a difficult time to twirl it as though it were a baton, and you won't be able to do it nearly as fast. And so that's what we mean whenever we say that there's a resistance to rotation. So rotational inertia depends on more than just mass, because in the broom example, the mass didn't change. Only the axis of rotation changed. And so that's what this discussion in this video is going to be all about. It's just getting behind the concept just a little more deeply, because we're not really going to do a whole lot with coming up mathematically or deriving moments of inertia in this course. In AP Physics C, we look at it so that we can figure out how to do it for any object. But we're just going to stick with the simple cases in this course. So what I've drawn here is just a disk which is going to rotate. And if you prefer to think of this as just a long stick, then I drew that line in there as well. But our axis of rotation is going to be at the center right here. We're going to make this our axis of rotation. And we're going to pick 2 points. We're going to pick this point and then one all the way out here at the edge. Now these 2 points have two different radii, or they're 2 different distances from the axis of rotation. So the inner one is obviously closer to the axis of rotation, and the outer one is further from the axis of rotation. And so what we're going to do is just take a look at what's going on. Now, the moment of inertia for each particle is going to be, if we only look at just this little chunk right there, it's just a point particle, all right? The moment of inertia, we already said whenever we derived Newton's second law, was going to be mr squared, okay? And just looking at the mathematical definition, we can see that the distance r from the axis of rotation is what is going to cause the moment of inertia to increase for a chunk of material, but not something which is extended in 2 or even 3 dimensions. Okay, so why is this the case? Well, the first thing to keep in mind is that the angular velocity is the same for each. Now, what that implies is that both objects complete the circle in the same amount of time. And that is critical because now we get to look at this from a couple of different perspectives. If we look at this in terms of forces, or I should say kinematics, what we find is that the particle that's on the inside has to travel a smaller distance. So distance for the inner, or the arc length for the inner, is equal to 2 pi r, because it's just going to be a complete circle as we go around. So that's just going to be the circumference, 2 pi r, and this is going to be a small number, and then the distance for the outer is going to be 2 pi, and I'll label that capital R just to denote that it's a larger distance. So if that's going to happen, then this implies that the velocity here is small and the velocity here is large. Okay, so small velocity, large velocity. In terms of kinematics, what we're able to say then is that the tangential acceleration is going to be small when r is small, and the tangential acceleration is going to be large when r is large. Now, that further implies that it's going to take a larger force to make the one on the outer edge accelerate and a smaller force to make the one on the inner edge accelerate. We can look at this in terms of torque. If we look at the torque of it all, we know that torque is equal to R times F, and each chunk is going to have the same pull of gravity on it. And so the torque required to make them move around in the circle is going to be different because R is bigger for the one closest to the outer edge, and R is smaller for the one closest to the inner edge. Perhaps the one that's maybe easiest to understand is if we look at it from an energy perspective. If we look at this in terms of energy, then what we can say is that this chunk that's closest to the inside, being that it has a smaller tangential velocity, implies that it's also going to have a smaller kinetic energy, because the kinetic energy for the chunk is just equal to 1/2 mv squared. And so the chunk on the inside edge is going to have less kinetic energy. The chunk on the outside edge is going to have more kinetic energy. That means there's going to have to be more work done for the chunk that's on the outer edge. And because they both complete the circle in the same amount of time, that work must happen at a faster rate. Or the proper term for that is power. We need more power to get this outer chunk around in the same amount of time as the inner chunk. So the inner chunk takes less power to make it go around. And with more power means you have to have larger forces, etc., etc. Okay, so that's the idea behind moment of inertia. So we're not going to be deriving the equations for the common moments of inertia, but I am going to give you a very short list for the common moments of inertia. Now, you don't have to memorize these. They're always going to be given to you, or you're going to have the opportunity to look it up in a table. And there are many of them, but I'm only going to give you a few. The first one I'm going to give you is I is equal to mr squared. And this is valid for one of two geometries. It's either a point particle, or you may think of it as a small chunk, or it applies to what we call the thin ring. And the thin ring is basically like the rim on a bicycle wheel, something that's very thin. So a thin ring would be what I can draw like this with a line. A thick ring would look something like this, where there is a thickness dimension to that outer edge. And we're not looking at that. We're looking at only the mass being put all on the outer edge. So that's all we're interested there. Now, why is it that it's the same for a point particle or for the thin ring? Well, quite simply because in either case, whether it's a chunk all the way out here at the edge, where this is equal to m total, right? Or I take the entire mass of that chunk and I beat it into a thin line, a thin strip, and put it all the way out at the outer edge. In both cases, all the mass is located the same distance away from the center of the circle, from the axis of rotation. So that's the only thing that matters. Now, we also have I is equal to 1/2 mr squared. And I equals 1/2 mr squared, this is going to be for a solid disk. Okay, so that's basically what I drew here. So if you were to take a baseball bat and you cut the end of it off, you would end up with a disk. Okay, then we have I is equal to 2/5 mr squared, and this is for a solid sphere. And then finally, the last geometry that we see a lot is going to be for the long thin rod, and that will be 1/12 ml squared. Because we're looking at a thin rod, it has a length. We don't tend to think of it as a radius. And so this is going to be the long, thin rod. Okay, now one more really important thing about this, and that is that all these moments of inertia, the axis of rotation is through the center of mass. That's really, really important, because in the next video I'm going to take a look at the parallel axis theorem, and we're going to have to distinguish between the cases where the axis of rotation is through the center of mass and when the axis of rotation is through a completely different point.